Good afternoon, students. In afternoon session, we have discussed about the topics of difference between interference and diffractions. It is very difficult to distinguish between interference and diffraction as both exhibit have the wave nature of light. In both, the phenomena of the light reaches in geometrically shadowed region and also interface to produce maxima and minima. Nevertheless, based on the appearance, the difference was given in a tabular column of 6.5. So simply, what are the differences between interference and diffractions? First of all, interference. Interference means superposition of two waves. Diffraction, bending of waves around its edges. In the second point, superposition waves from two coherent sources. We know that coherent source is nothing but the wavelength and phase will be same. In diffraction, superposition wavefronts emitted from the various points of the same wavefront. And third point, in interference, equally spaced fringes. In diffraction, unequally spaced fringes. On interference, the intensity of all the bright fringes almost same. Here, the intensity falls rapidly for higher orders. Finally, the large number of fringes are obtained. Here, less number of fringes obtained. And further, we are going to see, which means here, polarizer and analyzer. So let us consider as an unpolarized light. This is a source of unpolarized light. It is in a beam of light. The vibrations can be in all possible direction of the propagations. Shows in the figure 6.74. When the light passes through the Polaroid P1, which means when the light passes through the Polaroid P1, the vibrations are restricted to only one plane, which means only allow the particular plane, the emergent beam from P1. The emergent beam can be further passed through the another Polaroid, which means other Polaroid. It's rotated about the ray of light axis for a particular position of the P2 intensity is maximum. When the Polaroid P2 is rotate from the position of intensity starting decreasing. So there is a complex extensions of the lights of P2 here. So further rotations of P2 is reappears the intensity of increase becomes of maximum. Further rotations of throw 90. So intensity will be high. The light coming out from the Polaroid P1 is said to be a plane polarized. So here at this point, the light coming out from the Polaroid P1 is said to be a plane polarized. The Polaroid P1 which plane is called as unpolarized light. So the passing through is called as polarized, and the Polaroid P2 which acts as the examiner with the beam of light is called as analyzer. So the Polaroid will be act as a polarizer and also as well as analyzer. In second, plane and partially polarized light. In a plane, polarized light is the intensity varies from maximum to 0 for every rotations of 90. So the diagram tells us the vibrations are allowed in one axis and completely restricted to the perpendicular axis. On the other hand, second one, And the intensity of light varies between maximum and minimum for every rotations of 90 degree of the analyzer. So the light is said to be a partially polarized light, shown in the figure of second one. This is plain polarized light. The second one is partially polarized light. Next topic, Morley's law. Figure 6.76 tells us the explanations of Morley's law. Whether here this is an unpolarized light. The unpolarized light seen through the analyzer, the intensity is transmitted varies the light as the analyzer is rotated through the angle of perpendicular. So in 1809, French physicist Ian Morley discovered that when the beam of plane polarized lights of intensity I0 incident on the analyzer, the light transmitted the intensity of the I from the analyzer varies directly square of the cosine angle between the transmission of axis of the polarizer. This is Morley's law. So we can write as Morley's law, whereas here I equal to I0 cos square theta. So we can simplify that the equations. I directly proportional to E cos square cos whole square. We can change the proportionality symbol. So providing equal sign and proportionality constant, and E cos theta whole square where carries the proportionality constant, squaring the terms. I equal to k e square and cos square theta, whereas I equal to I naught cos square theta, whereas I naught equal to k a square. So this is the diagram for Morley's law, plane polarized light and plane of the analyzer. So both things of provided here provide two cases. The first case is when theta equal to 0, cos 0 becomes 1, then I equal to I naught, because of cos 0 becomes 1. Then case 2, theta equal to 90 degree, cos 90 becomes 0, so 0 into any number 0, so I equal to 0. So first case tells us the transmission of the axis of polarizer is along the analyzer. The intensity of the light transmission from the analyzer is equal to the incident light, which means I equal to I naught. Second case is whereas I equal to 0. So the intensity of transmitted light from the analyzer becomes 0. Our next topic, uses of Polaroids. The first point, Polaroids are used in the goggles in cameras and avoid the glare of light. Goggles means nothing but sunglasses. So the glasses which helps to avoid the glare of light with the help of Polaroids. The second point, Polaroids are useful in three-dimensional motion picture, which means holography. Third point, the Polaroids are used in improve the contrast in the old oil paintings. And then Polaroids are used in optical stress analysis. And fifth one, Polaroids are used as a window glasses to control the intensity of the incoming light. So avoiding the incoming intensity of incoming light. And sixth one, polarized laser beam acts as a needle to read and write the compact disc like a CD. And finally, Polaroids, they produced polarized light to be the used in a liquid crystal display LCD. And then polarization by reflection. It is the simplest method to producing of plain polarized light by the method of reflection. Here, let's see the diagram very carefully. Here, first of all, AB. This is AB is an incident and unpolarized light at the angle of and reflecting layers of X and Y. Okay. So the vibrations here, The vibrations AB, which is parallel to the plane of the diagram shown by the arrows. The vibrations which are perpendicular to the plane of the diagram and parallel to the reflecting surface. This is XY by the reflecting surface shown by the dots. So a part of light is reflected along BC. A part of the light is reflected along BC and rest is refracted along BD. So on examining the reflected beam BC with an analyzer, is found the ray is partially polarized. This is a partially polarized light. When the light is allowed to be the incident of a particular angle, reflected beam is found to be a plane polarized. So the angle of incidence at which a reflected beam is plane polarized is called as polarizing angle IP. So this is the based on Brewster's law. So Brewster's law. To write the Brewster's law, you must draw the diagram necessarily. Okay. So first of all, Brewster's law. In 1808, Morse discovered when an ordinary light on the incident surfaces of the transparent medium, it reflected light partially plane polarized and extend the polarization depend upon the angle of incidence IP, and particular angle of incidence that reflected of the light found be a plane polarized, which means dot lines. An angle of incidence of the beam will be unpolarized following the transparent surfaces of reflecting beam of the plane polarized light is called as polarizing angle IP, or as called as Brewster angle. Okay. So further, the British physicist Sir David Brewster found that the incidence of the polar angle, the reflected transmitted rays are perpendicular to each other. So suppose we have right as the IP plus 90, RP becomes 0. So we are moving this 90s then another side of the equation. So RP, which means RP here and IP goes that side. So 180 minus 90 becomes 90. Then after RP the sequence becomes minus IP. So according to Snell's law, refractive index n equal to sine of the angle between of polarizing angle and RP. So here RP, put the value of RP in this equations of Snell's law. So substitute the value here. So sine IP, sine 90 minus IP equal to cos IP, sine IP by cos IP equal to n. So tan IP equal to I. So the relation tells us finally Brewster's law. This law states that the tangent of the polarizing angle of a transparent medium is equal to the refractive index. This is value of the Brewster's angle depend upon the nature of the transparent refracting medium. Okay. And then next topic, and the important topic also, pile of plates. Okay. So let's see the diagram here. So see the diagram clearly. First of all, the phenomena of polarization by reflection used for constructions of pile of plates. Okay, it consists of number of glass plates placed one over to other in the tube. This is a tube. The glass plates are inclined at the angle of 33.7 degree to the axis of the tube. The beam of unpolarized light is allowed to fall off a pile of plates and the axis of the tube. So the angle of incidence of the light will be 56.3, in which the polarizing angle. So this is the polarizing angle of the glass. So the vibrations is perpendicular to the plane of the incidence that are reflected on the surface, those parallel to the transmitted. So the larger number of surfaces, greater intensity of the reflected plane is polarized light. So the pile of plates will be act as a polarizer as well as analyzer. And finally, we are going to see the topic of optical instruments. There are plenty of optical instruments we are used in our daily life. We shall discuss here about microscope, telescopes, spectrometer, and of course human eye. So first of all, we have discussed simple microscope. So simple microscope will be a single magnifying converging lens, which means converging lens is nothing but convex lens. The magnifying lens of small focal length. The idea is to get erect and magnified and visual image of the object because of we are using a convex lens. For this object is placed between F and P. Principal focus in pole of one side of the lens and viewed from other side of a lens. There are two magnifications to be discussed, two kinds of focusing. First of all, near point focusing. The image is formed at the near point, that is 25 cm for the normal eye. The distance is also called as least distance, D, of distinct visions in the position of the eye feels comfortable, but there is a little strain on the eye. This is shown in the figure of here. Eye focused on the near point. It makes some strain to the eye. Okay. And then the second point, normal focusing. So the image formed at infinite distance. In this position, the eye is most relaxed to view the image. Most relaxed view the image. These cases. So magnification in near point of focusing. The near point of focusing shown in the figure 6.83, already we have seen it. The object distance U, the distance between lens and the object, and the image distance is near about D. This is a near image distance. The magnification formula, we know that magnification M equal to V by U. So with the help of these equations of lens formula, 1 by V minus 1 by U equal to 1 by F. So further, the magnification can be simplified. We can written as M equal to 1 minus V by F. So substituting V for the sign conversions, V becomes minus D because of left side of the lens. So magnification M equal to, here V will be having minus sign and also here minus. Put the value from here, M equal to 1 plus D by F. This is the near point focusing. So, and second one, magnification in normal focusing of angular magnifications. So the normal focusing in the shown in the figure of 6.84b. This is 6.84b. The normal focusing. We will now the magnification for the image formed as infinity. If we take the ratio of the height of the image to the height of the objects, here magnification represents as h dash by h to find the magnification. We will not get the practical relations as the image will be also infinite size when the image formed at the infinity. Hence, we can practically use together the angular magnifications. So angular magnification is defined as the ratio of angle theta is subtended by the image of aided eye to the angle of theta naught subtended by the object unaided eye. So magnification we can write as theta I by theta. So tan theta approximately equal to theta naught. So h by d unaided visions. For aided eye show figure 6.83 theta I equal to I is equal to h by f. So theta I by theta equal to h by f divided by h by d. So simplify the terms h will be cancelled. The reciprocal equation magnification becomes d by f. So this equation tells us the magnification for normal focusing. The magnification is a normal focusing is 1 less than the near point of focusing. But the viewing is more comfortable in the normal focusing than the near point of focusing. Here the value of df in the magnifications of usually small. This is considered as a normal focusing.